So I have one correction. I've handed out homework 3. So the first correction for homework 3 is that I made a mistake in reading my calendar, and the due date is not this Friday, but it's actually next Friday, so it'll be home. There shall be no homeworks due in less than 7 days in this class, and I shoot for 7 to 10. All right, so what are we going to do in this class? We are going to start a new technique, a technique that, just like divide and conquer, it's a pervasive technique. It'll be used for many interesting and practical algorithms. A lot of the programming contest problems fall into this category. It's called dynamic programming. And I'm going to give you, in the next 3 lectures, 6 examples, ranging from very simple ones, getting progressively more and more complicated, to illustrate this technique of dynamic programming. Today I hope to give you a log cutter example, matrix chain, and a typesetting example. But I'm going to start with a different problem, a problem that actually you might encounter, for example, in one of your interview questions. I'll start with a personal detail. Although the picture is not coming out correctly, as I grew up in Texas, I always had a house with stairs in it. Then when I went to college, I always lived in dorms that had stairs, not elevators. And then when I went to live in San Francisco, I've always had houses with stairs, not elevators. And then when I went back to grad school, I also lived in a 5-story walk-up. And then after grad school, when I lived in Zurich, which is where this is from, every one of my places were 4 or 5-story walk-ups. So I've always had stairs in my life. In fact, the first place that I moved that had an elevator in the place that I lived was, in fact, Charlottesville. So the question I pose to you is, if you have a lot of stairs to climb in your life, you might think about natural problems. For example, oftentimes when you're climbing stairs, you take either one step, you start here at the ground floor, and you either take one step, or sometimes you take 2 steps. Right? So you either take one step at a time, or you jump steps. Now imagine you have n steps, which in my case, in my Zurich flat, I had 98 steps to walk every time I needed to go to the grocery store or do anything outside. So if you have 98 steps to walk up to get to your apartment, and you can take essentially steps, you can either take single steps or double steps, how many possible ways are there to climb to the top of your house? Spend a minute and a half, 2 minutes, with your neighbor, talking about how many ways there might be to climb up to the top of, if you have an n-story staircase, and you take either 1 step or 2 steps at a time, how many ways are there to climb? Now let me give you an example. For example, one way to climb would be 1, 1, 1, 1, 1, 1, right? So you just take 1, etc. Another way to do would be always take double steps. Another way would be to take a first double step and then all ones. Another way would be to take 2 double steps and then all ones, or take 1 and then etc. So I would like you to count the number of ways there are to get to the top of your staircase if you're taking only onesies or twosies. The type of question you might encounter in a Google or McKinsey or D.E. Shaw interview. Spend 2 minutes with your neighbors. You cannot go backwards. Okay, I hope you've had some time to think about this problem. And I hope that you remember, when you encounter similar problems at your job interviews, you will remember this algorithmic thinking, or this, this idea of breaking a big problem into smaller problems. So this is a good interlude into the new unit that we're going to do, dynamic programming. So the way one might approach this is to say, well, this right here, how many ways there are to climb n steps, I'm going to call that T of n. So T of n is going to be the number of ways to climb n steps. And now, this is going to be a technique that you often use in dynamic programming. You think, if I were at the top, if I was here at the top, that very last action that I did, what did I do? I either took a single hop to get here, or I took a double hop to get here. And so the number of ways to get to the nth step is going to be the number of ways to get to the n minus first step. I'll write that in red so it's the same color. Okay? So this is the number of ways to get to right here and then taking that one red step, plus the number of ways to get right here and take a double step. So the insight was, think if you're at the very top, what was the very last thing that you could have done? You could have taken a 1 or a 2 step. And then, how did you get to that spot? Well, that's where the recursion comes in. Now you're going to, again, apply the same thing. Now this right here is a recurrence. And we've solved several forms of recurrences, but we haven't yet solved these type of recurrences. Question? Y plus 2? Gotten to which one, the blue or the red? The final one. Well, the two different ways are either you came along the red path and took a 1, or the blue path and you took a 2. So this recurrence right here is actually a famous one, made famous by an Italian who was studying the number of rabbits that he would have in his field. And this guy was named Fibonacci. Okay? So of course, if you have 98 steps, you have a lot of ways to climb to the top of your apartment. Even if you have 20 steps, 2 stories, you have plenty of ways. Because this Fibonacci recurrence, it actually grows. This right here is the golden ratio. And this number grows as basically phi to the n. Okay? Now, how am I going to use this to... Here's a simple program to actually compute this number. And I think someone over there found this program as well. And the reason I think this is a really good introduction to dynamic programming, let's think about if you wrote Fibonacci in this way, what the running time of this algorithm would be. All right, so this would be the simple way. This is exactly how the recurrence is specified, and so we're implementing it exactly how the recurrence says. In divide and conquer, when we came up with an algorithm or a recurrence, our implementation exactly mimicked the recurrence. So this is if that was our lesson, this is what we're doing here. Let's take a look at what happens. So let's say we start with stairs of 5. Now that's going to make 2 recursive calls, stairs of 4 and stairs of 3. But of course, stairs of 4 is going to be evaluated first, and then we're going to make recursive calls like this. Okay? Now notice that when the recursion comes all the way back up to S4, we are then going to do the recursion for S3. Even though we've already computed here, the way we've implemented it is actually going to make exactly the same calls. If you count how many, let's imagine that the running time of this program is actually all in the setting up of a recursive call. So a function call in C, it takes a little bit of, you have to move your stack pointer and you have to do a little bit of stuff in order to expand your stack and make a recursive function call. So imagine that's all the work that's going on here. In order to compute stairs of 5, it's going to take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 recursive calls. If you generalize this, if you compute stairs of n, right, what do you think, how many recursive calls do you think are you going to make? Right, think for example, S of 6. That's going to make a recursive call to S of 5 and S of 4. This, you already know how many calls it's going to make. And this is going to make some other number, right? So in this case, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So S of 6 is going to be 9 plus 15, right? S of 7 is going to be S of 6 plus S of 5, right? So the number of recursive calls in this algorithm is also going to be related to the Fibonacci number. And therefore, it's going to be somewhere around phi to the n. So the point of this aspect, of this part right here, the point of this slide is to say, if we were to implement the function that would compute the Fibonacci number, the nth Fibonacci, in the most naive or the most clear recursive formulation, then the amount of work that we would do would be related to the Fibonacci number. So it'd be exponential work to compute a function that's actually quite simple. Now, as a computer scientist, you must have a natural instinct on the right thing to do. What's the right thing to do here? So as a mathematician, you'd want to find a closed form. Now, in fact, the closed form for Fibonacci does involve 1 over square root of 5. There is such a formula. The thing is, Fibonacci is a discrete number, right? It's always going to be an integer. The closed form involves an irrational number that you have to compute with. So it's to get a very precise computation of the, let's say, 1,000th Fibonacci number, using the closed form requires very precise, floating point calculation. So let's try to limit ourselves to discrete methods that we've talked about so far. Perfect. And that's exactly the number one rule of dynamic programming. The one insight is that you'll often encounter problems like this where you continue to refer to values that you've already computed. And so the way you're going to deal with those things is to not just recompute them on the fly, but to be smart about it and remember those answers and refer to them when you need them. So, in fact, this is a better animation. So what you're suggesting is, okay, so we're going to handle the base case as we did before. Okay, and if M contains n, return M of n. Otherwise, basically you're going to set answer equal stairs of n minus 1 plus stairs of n minus 2. And then you're going to set and then return the answer. This is just an implementation of exactly what you said. Initialize some memory at the beginning, and then remember the answers that you compute. So let's go through this example. I will put that. Let's now see how this memoization will help in this case. So if we had stairs of 5, we'll run through this line and this line. Our memory at this point, let's put M right here. It's all blank. So we're going to execute this line right here, which will make a recursive call to stairs 4 and stairs 3. But it's going to evaluate stairs 4 first. Question? Smaller? That's right. We can do a slight optimization by changing this order. But in fact, we're going to come to something even better in the next slide. So this is just a stepping stone to a much cleaner implementation. What I want to do is, of course, illustrate the fact that saving these values, of course, is going to make the computation much, much faster. So this will compute stairs of 3 and stairs of 2. Okay. So finally, when this recursive call calls S1 and S0, these will return 1 and 0. And then this line right here, the red line, will set S2 to basically be 1. And it will return 1 here. This will also return 1 since it's the base case. And then at this point, we'll fill out S3. Question? You're right. Good point. So then all of my answers will be wrong. So right, this recursive call will then fill out S4. And then now when we come to S3, since we already have the answer, this will return the right answer. Now, why did I put this slide up here? I wanted to show, we started off with a clean recursive implementation of the stairs number. And then we realized we're doing too much work because we're recomputing things we've already computed, so we added a memory. And in fact, this is what our solution came out to be. But notice that the way that we filled out our memory, we started right here, and then we filled out this value, and then S3, it depended on these last two values, and so we filled out S3 at this spot. And S4, it depended on these last two values, so once these two values were computed, we're able to compute S4. So in fact, if we just look at the order in which we fill M, there's actually a much simpler way the thing that you would probably actually implement in practice. If I were to give this as a homework problem, you would make some for loop, and it would probably look like this. Stairs 0 is equal to 1, stairs of 1 is equal to 1, and then now, for I is equal to 2 to n, stairs I is equal to stairs I minus 1 plus, right? This is probably what you would have done, right? The only reason I went through this is because when we encounter more complicated examples, examples that you might not immediately see that you could do this with, you should still get used to the thought process. The thought process is that we started with a purely recursive formulation. We realized that we should memorize or memoize intermediate results. That led us to this. When we actually thought about it some more, we realized that the order of that memoization is all that mattered. We didn't have to make all these recursive calls. We could just solve the problem by noting the way that the memoization array is filled and just fill in that array directly, which led to this final algorithm. So those two ideas are already in dynamic programming. The big ideas are that a problem has some recursive substructure. Okay? In this case, it meant T of n was equal to, okay? So the point is that the optimization problem that we're trying to solve has some sort of recursive structure. The solution of a problem of size n can be expressed as some function of the solutions of smaller problems. And the second big idea is this memoization, is that we keep track of intermediate results, and going one step further, we solve the intermediate problems in a specific order to maximize efficiency. So let's highlight this technique with our first bona fide example, non-trivial example of dynamic programming. And that is the woodcutter problem. So if you like to do woodwork, if you like to make furniture or make objects, you know that when you take a log and cut it into lumber, there's several ways you can do it. So for example, here you quarter saw, if you cut the log like this and then take your boards like this, it's called a quarter sawn log, and it gives you a grain pattern that looks like that. A much simpler and crude way to cut a log is to just regular saw it like this, and then you'll see the grain structure basically looks more flat like that. This is all to motivate the following optimization problem. So suppose that you had just felled a very large piece of lumber, like these two fellows right here. And now you're deciding that you want to sell this lumber to very high-end furniture makers. You can see this log is like 6 feet in diameter, and that people buy, dining tables that are made of a single slab of wood. It, has a very nice grain pattern, and probably the tree right there was 250 years old. So, you can imagine the kind of people that like to spend their money on such artifacts. And so such a table is going to be very expensive. You don't want to just cut this log up in any arbitrary way. And the hedge fund approach to this would be, let's first investigate the spot market price for lumber. So for example, there are prices for 1-inch boards, 2-inch boards, 3-inch boards, etc. Let's call this P1, P2, P3, okay? So PI is basically the spot price for an I-inch wide slab of lumber. PI is the spot price for an I-inch wide slab of lumber. And that suggests the following log cutter dilemma. So the input to the problem is going to be the size of the input log. So you have an n-inch wide log that you need to cut. You're also given the spot prices for all of the slabs of width 1, width 2, width 3, etc. And your goal, as any capitalist, is to maximize profits. And that means that you want to find a set of cuts, so there could be k cuts you want to find, such that, of course, each of the cuts, you only have n, your log is only n inches wide, and so the cuts that you make have to, of course, fit into the log, and you want to maximize. So let me give you an illustration of why this problem is not trivial. So if we go back to this slide right here, okay, it's very conceivable. So suppose n was equal to 5. So the question is, do you cut it as P1 and P4, P2 and P3, or basically P5? So it could be that the most money you make is by splitting your 5-inch board into a board of size 2 inches and a board of size 3 inches. In another situation, it might be better to make a 4-inch board, or in another situation, it could just be that 5 is the best price. Okay? And now if you have something like, 200, if n is equal to 200, now you can sort of see that the problem becomes much more complicated. Because so if you have a very wide board, you wouldn't know whether to cut them all into 1-inch slabs or several two. You sort of see the same flavor that we have in the staircase problem. In that staircase problem, I artificially said you could only take 1 step or 2 steps, not 3 or 4, right? But in this case, question? So indeed, let's imagine that all of these have to be, you can basically generalize this to be a 3-dimensional problem. But now let's generalize it into, let's just consider the very simple case where the only decision you make are the width of the planks. They're all the same thickness. But that's, of course, a natural generalization. If you really have a big log, you really need to figure out the right pieces to cut out of that. You can also imagine, for example, diamonds. If you are a miner of diamonds, when you get a big diamond, you have to, first of all, the diamond is raw. You have to figure out, when you have a big chunk of diamond, people have to cut these diamonds. And so the first thing you have to do is figure out how many small diamonds you're going to make based on the fractures in the, based on the imperfections of the stone, etc. You fracture this diamond into smaller pieces, and then you individually polish them and so forth. And of course, you want to make the most money out of that raw diamond. Same sort of problem that this is trying to reflect. It's an optimization problem. How do I split something big into smaller pieces that maximizes my revenue from them? Let's consider the simplest example, this. Okay? So does everybody have a feel for the complexity of the problem? If you had n is equal to 200, and I give you prices from 1 to 200, you have to figure out what the best way to divide that log would be. You can't try every single possible combination, as we saw with the staircase problem. Just considering 1s and 2s and 3s, and for example, gets you to too many combinations. All right? So this is what I want to do. I want to introduce the way that you think about problems that are phrased like this. And it's going to go back to what you did with the staircase problem. What did we do to crack that nut? We basically said, what was the last action that I took when I got to the top of my staircase? So now imagine that I have a log, okay? And imagine that I actually knew what the best solution was. That best solution, you have to imagine the very last cut that you make in the best solution. Let's call that IK. What has to be true for IK to be the best solution? It basically has to say that the best way to divide an n-inch log must involve, the very last cut was of length IK, so what I'm going to make from the best solution for cutting this log is going to be the amount of money that I get for that slab plus what? Exactly. And this is where the recursive structure is coming into play. If I'm looking for the best way to cut the n-inch log, then my very last option, my very last cut, if we call that of length IK, it has to be such that the total amount of money that I get was the price I had from that last cut plus the best way of dealing with the log that was this wide. Right? If there was a better way for dealing with this half, then of course I would use that better way and get more money for that log. Okay? So this observation, it suggests an approach to a solution. So we know that the best of n is going to be pik plus the best of n minus ik. And now we also know something, which is how many possible cuts are there for you? That last cut, how many options do I have at that spot? You have basically n, right? Or n minus 1. So this suggests that the best way of dealing with n is going to be, let's try every single possible cut. The best way of splitting that n-inch log, so in other words, the best way to cut a 200-inch log is basically to consider making a 1-inch cut and then cutting a 99-inch log, is to consider these n options. So the first step in solving these type of dynamic programming problems is to come up with an equation like this, which reflects the recursive substructure. And now the second step is to remember how to use memoization. Because notice that b of 199 is also going to require 198, right? Because this is going to be 1 plus b of 198, 2 plus b of 197, right? So just like in the staircase problem, this is going to be like a staircase problem, but it's going to have a much, much larger branching factor. In stairs, you only tried minus 1 and minus 2, right? Here, you're going to be trying every single possibility at every step of the tree. Okay, so we're getting close. We're getting towards a solution. If we think about the way in stairs we had a memory, M, that kept track of prior solutions. Now, think about, right, the equation tells us that position n is going to require essentially looking at all of the previous positions, right? And so what that suggests is that the way to solve this problem is to start at this end and incrementally compute each of these values. Because the ith position, it's going to require the previous I minus 1 positions. So let's start by computing from the extreme left and incrementally updating this table. Right? So that suggests an approach like this. So we say that best of 1 is basically going to be p of 1 plus best of 0. So this is just going to be p of 1. Now, best of 2 is basically going to be, it's going to depend on those two values. It's going to be the max of p2 plus b0 or p1 plus b1. And you fill that position in right there. Right? And now b3 is going to be the max of p3 plus b0, p2 plus b1, p1 plus b2. Spend a minute with your neighbor. Based on this insight, write the algorithm for solving the log cutter dilemma. All right, let's regroup and take a look at one possible solution here. So the idea is that we're going to start in this array right here. This array B is going to store the best way to cut a log of size I. And so, of course, if you have a log of width 0, the most money you can make from that log is 0. If it was anything more, I would be a very wealthy person. So we're going to start here with b0 is equal to 0, and then we're going to iteratively update this, where essentially we're going to go from 1 to n, and bi is going to be the max of pj plus b of I minus j. Okay? This is what the mathematical expression was. If you were to just write that into a C loop, you would essentially initialize bi to some very negative value, like negative infinity, and then just loop from 1 to I, where you create some temp variable which computes pj plus this value. And of course, if this value is greater than what you currently have, you store that value. Now, what is the running time of this algorithm? How many times does this loop run? N times. And notice that this loop right here is going to go from 1 to I. Right? So the running time is going to be, the first time it's going to go through the loop once, then it's going to go through it twice. The last time it's going to go through the loop n minus 1 times. This summation should be familiar. It should be roughly theta n squared. Any questions about this? Question? Can you do it better? I would have to think about it. I would have to think about it. With these type of problems, it's conceivable. You could go to n log n or n. I'm not sure. But the point for this class is just, these are stepping stones. Just like with stairs, we did that in order n. There's actually a way to do that much better, to compute the nth Fibonacci number. So there might be a better way to do this. But what I want to introduce, just with these simple examples, is this idea of dynamic programming. If we recap, what did we do? We started the problem staring into this combinatorial explosion of, we could have like 14 of these type of things or 12 of that, and if you were to think about it in some ad hoc way, you'd be overwhelmed with the number of ways you can divide that log, and how would you keep track of all of those ways? We stepped back and thought, you know what, the very last action, the very last cut that we're going to make on that log has to be of some width. Let's call it, and let's think about that. It has to be of a width such that when I leave the rest of that block and cut that rest of the block optimally, the number I get is the maximum. And that led us to this expression, this optimal expression right here. And once we came to this conclusion right here, we figured out a clever way of implementing it in an array like this that gave us an n squared algorithm for the problem. Those are the 3 steps. Think about the very last step. Come up with a come up with a solution that illustrates the recursive substructure, and then come up with a way of organizing that, the subproblems, so that you solve them in the right order, so that the solution becomes simple. Question in the back. One second. I've just figured out how to make those microphones work, so push the gray button and say your question so that it gets recorded. Very good suggestion. So what you're saying is, let's look at the average value per inch and then pick the width that has the highest one and continue in that way. And that's a very good idea. That approach is called a greedy algorithm. And a greedy algorithm is not going to work in this case. In fact, your first instinct with many of these dynamic programming problems is to use a greedy algorithm. In the homework, I try to go through this theme by the last problem essentially says, consider a greedy approach, and show an example of why that doesn't work. So the same situation will arise here. You won't get an optimal solution basically because of rounding issues. I could come up with a problem instance where some width has the highest average price, but if you were to use just entirely that, if you were just to use that width, you would have some leftover that gives you a globally inferior solution. Question? Very good question. Very good question. So again, I'll repeat the question. If you don't push the button, please remind me to repeat the question. Do we have to just return the actual value of the log, or do we actually need to return the cuts that you need to make? What I'm going to suggest is a one-line addition to this algorithm will actually produce that list. So oftentimes in these dynamic programming algorithms, just computing the actual optimal solution is enough to figure out what the right choices are. So what I'm going to suggest is that at this spot right here, in fact, let's keep another array called choice inside this inner loop right here. We're going to keep another variable, choice I, and it reflects whichever k was chosen for the max here. We just keep track of what that k was. So essentially whatever k set the maximum right here, we keep track of what that index of that k was. So now what we can do is look at choice of n. That's going to tell us what the maximum, the actual width of the maximum value at that choice. It tells us exactly what the choice is that we made at the nth step. Then if, let's say that was like 4. Then we can go to n minus 4 and look at the choice that was made at that step. That'll tell us the best choice and so forth. So in other words, this is just going to keep track of a set of pointers which gives you the chain that led to the best actual outcome. Very good question. Question. That's a good question. So in this case, P has to be positive. Otherwise, there isn't a... no, that's not true. There are no constraints on the pricing matrix here. Even if you can imagine, if the prices were negative, you would never select that, because then you'd be selling a chunk of wood and actually having to pay someone to take it for you. So it wouldn't, you're better off doing nothing. Yes, question? Okay, so this right here, the particular value of k that resulted in the max at this step. The particular value of k that resulted in the max during this computation. So while you were going through this, this is a loop, right? This is a loop right here, let's say. I've changed variables here, but whichever value of j went from 1 to I, at some point, this loop had its maximum. That index where it was maximum, I'm going to call j star. And now in this slide, I'm going to change variables and call it k star. Did that make sense? This is a note to myself. I'm going to work out an example and try to post it for some, like, let's say, larger scale problem so you can sort of see. Okay. Mm-hmm. Yeah. This is just the smallest number. It's just a convention because I want the very first step right here in order to set it to t. But this loop will work if you set this to 0 as well. This one? Can you push the button?
Does choice I tell you every choice you have to make, or just would choice n be just the last choice, or would it be...
Yes, great question. Choice n would be the choice that you made at position n. Let's imagine that that choice was 4. Then what you would do, after you know that the very last cut you made was with 4, you would then go to choice of n minus 4 and see what choice you made at that spot. And you would run that all the way down until you get to 0. And those are all the choices that you had to make in order to get an optimal cut. Great questions.
So would some of the spots in the array be empty?
Will some of the spots in the array be empty? Every single spot will be filled, because this loop is starting from I to 1 to n. So it's going to go through every spot, and it's going to set best of I to something. The next example, I'm only going to introduce in the last 5 minutes, it's going to get more complicated than this log cutter. It's going to be a two-dimensional version of dynamic programming. Every one of these examples is going to grow in complexity just by a little bit. Let me set up the problem in the last few minutes of class. So we all remember matrix multiplication from divide and conquer. If you have a matrix of this size, let's say this is R1 and this is C1, this is R2 and C2. First question, how big is the resulting matrix? How many rows will there be in this resulting matrix? R1. And how many columns? C2. Very good. So how many operations are going to be needed to compute this matrix? Right? This little red dot is going to take C1 operations, right? C1 has to equal R2 for this to be well defined. So that red dot is going to take C1 operations, and how many dots will there be? R1 times C2. That's the number of operations. which we already know, roughly n cubed. Now, imagine you have 3 matrices you want to multiply. Because matrix multiplication is associative, you can multiply them either these 2 first, or you can multiply them this way. So do these 2 first and then that one, or these 2 first and then that one. And why might this matter? Question? Exactly. So depending on the order that you choose, one way might be dramatically more expensive than the other. Let me try to illustrate with an example here. So imagine A1, A2, and A3 are set up in this particular way. If we were to multiply these 2 first, we would create an intermediate array that's of size 10 by 5. Okay? And then we'd multiply these 2. Let's figure out how many operations this would take. This would take 10 times 100 times 5 in order to multiply these right here. And then in order to multiply these 2 right here, it would take what? 10 times 5 times 50. So what do we have here? This is 5,000, and this right here is 2,500. So the total number of operations is going to be 7,500. Remember this number, because the following number is going to be much longer. Suppose we do it this way, these 2 multiplied first. We're going to produce an intermediate value of size, what? 100 by 50, right? So just multiplying these 2 right here is going to take 100 times 5 times 50. Okay? And already you can see that we've blown the budget, right? Because this number right here is 25,000. So just multiplying in the wrong order, already you could have solved it 3 times already in the time that if you took the wrong order, right? Again, multiplying these 2 right here is going to take 10 times 100 times 50, which is going to be 50,000. So the total number of operations is going to be much larger. Okay? So, what's the point of this? The order in which you multiply these matrices matter. What's the best order? That's the next problem we're going to solve. I'll see you on Thursday.